Okay. Is it? Where's the guy who always checks?
Already up there.
Okay. Should I share? Check if it's showing and let me know. You know, you are always reliable, so. Is it showing now? Okay. That's fine. Okay, so this is what we are going to do today. You have done it with Nika Hoja?
Yeah. Hypothesis, right?
No.
Yeah, we did chapter 5 to chapter 4. That's why I remember, because she explained.
You have done the hypothesis, have you done the assumptions? No.
That total sum square with the assumptions and the goodness of the statistics.
No, R squared.
Sorry?
Chapter 4.
You did chapter 4, not chapter 5, right? Yes.
I don't know.
Okay, no problem, it's fine. So today we are looking at classical linear regression model assumptions. By the way, you know these things, especially those of you from Bank 504. So, before we start, who has an idea of classical linear regression model assumptions? What are they telling us about?
Not elasticity. I think like.
Sorry? Pardon?
There's 11 assumptions.
Yeah, there are 11 assumptions, but these assumptions,
Normally,
why do we have them? Why do we have them? Why are they important?
To have blue.
What's blue?
According to Gauss-Markov theorem, blue is first linear regression, unbiased.
Unbiased. Oh, okay, that's right. Guys, you know, we have the ordinary least squares estimator, right? You know, I like writing. Ordinary least squares estimator. Okay. If we are trying to do a regression, we have ordinary least squares as a technique which we can use to do a regression, estimate a model. But ordinary least squares is not the only technique we have, right? As you know, we also have another technique which we call maximum likelihood. Let's say maximum likelihood. There are many techniques, more than one technique. Okay, so we have the Gauss-Markov theorem. I don't know if I spelled it correctly. Sorry? Somebody said something. Yeah, we are going to talk about it 20 times. 20 times and then we'll stop. So what is the Gauss-Markov theorem telling us? The Gauss-Markov theorem is telling us that the ordinary least squares estimator is the best linear unbiased estimator if certain conditions are satisfied, right? So if certain conditions are satisfied, then the ordinary least squares estimator will be blue, best linear unbiased estimator. Okay. But certain conditions must be satisfied. And these conditions, we call them the classical linear regression model assumptions. You said there are 11 assumptions, 10 plus 1, whatever. Some of these assumptions are related to the regressors, especially multicollinearity. Some of them are related to the residuals. And those are related to the residuals are very important, especially heteroscedasticity, autocorrelation, you know, these kind of things. Okay. Now, what's the meaning of blue? Best linear unbiased estimator. Of course, you know what linear means. Unbiased You have an idea what's the meaning of unbiased?
Related to the omitted variable.
Okay, first, what's the meaning of best? Best. If they say the ordinary least squares estimator is the best linear unbiased estimator, best.
The best one fitting the.
By best, we mean in the class of all linear unbiased estimators, it has the minimum variance. So there is a class of all estimators which are linear and unbiased. This ordinary least squares estimator will have the minimum variance if these assumptions are satisfied. So we are going to see some of these assumptions, not all, but some. Okay. So these are 5 of assumptions. The first one, what does it mean? It's in notation form, but who can interpret it for me?
The residual
E.
variance.
No. Expected value of UT equals 0. What's E? Expected value means mean value. So here the expected value of the error term or the mean value should be 0. What does that mean? What does that mean? Does it mean it will always be 0? Does it mean the value of the error term will always be 0? No, it will not always be 0. You will have some positive values, you will have some negative values, but some of them cancel each other such that on average it should be 0, right? What does this mean? The variance of the error term is infinite and constant, right? Yeah, it's constant. Forget about the infinite, it's constant. How do we call that? There is a term for it. Constant variance, how do we call it? Homoscedasticity, you forgot? If the variance is not constant, if it is unequal, it is heteroscedasticity. Okay. What's this? The covariance of UI, UJ equals 0. Covariance. UI, what's UI? UI is one error term. UJ is another error term, right? So the covariance of 2 error terms should be 0. What does it mean? It means the error terms should not be related to each other. So there should be no autocorrelation. Why are you laughing? Sorry?
Just trying to answer your question.
Sorry. So this is trying to tell us that there should be no autocorrelation. This is telling us that there should be homoscedasticity. This is telling us that expected value of error term should be 0. The X matrix is non-stochastic or fixed in repeated samples. By the way, by X matrix, we are talking about the regressors. You know, dependent variable is Y, independent variable is X. So the regressors should not be stochastic. What does it mean? It means they should not be random. Error term should be random. Error term should be stochastic. But regressors should not be stochastic. And what does this mean? UT
Not equal to the number of.
No. It means UT is error term, right? So this simply means error term should be normally distributed with 0 mean and constant variance. So basically, it should be normally distributed. So you know these assumptions. Okay. Now, for each of these assumptions, we're going to follow like a format, or let me say like a template. For each assumption, especially with the diagnostics, you need to know 4 things, four basic things. First of all, you should know how to detect it. Okay, for instance, let's take autocorrelation as an example. You should know how to test for it, how to detect autocorrelation. You should know the causes, what causes autocorrelation. You should know consequences, right? What are the consequences of using ordinary least squares in the presence of autocorrelation as an example, and you should know the solutions. How can we solve autocorrelation problem? So for each of them, you should know how to test or detect it, what causes it, what are the consequences, practical consequences of having this problem and doing ordinary least squares, and how can we solve the problem? So in general, we may encounter this kind of problems. The coefficient estimates are wrong. Of course, if these assumptions are violated, then most probably you will have wrong results. The estimates you have will be wrong. Associated standard errors are wrong, especially in multicollinearity. The distribution that we assume for the test statistics will be inappropriate, so hypothesis testing is invalid. And we can try to find solutions for these problems. We'll see. Okay. When looking at the diagnostics, we can talk of two types of distributions. We have an F distribution, and what's this? What's an idea of this?
Is it X squared?
What kind of distribution is this? How do they call it? I will spell it. I don't know how to pronounce it. Some people call it chi-squared. I call it, I don't know, is it chi-squared, chi-squared, whatever. But that's how it is spelled. So that's the symbol. Chi-squared, chi-squared. Okay, you can pronounce it anyhow you want. So we have an F distribution and we have chi-squared distribution. So we can use either of these distributions when talking about these assumptions. But typically, most of the times, these distributions give you the same results. For instance, on E-views, if you try to test for autocorrelation or heteroscedasticity, you will get the results of the F test and the chi-squared. So you discover that most of the times you get the same results for the hypothesis testing. Okay, but if you have a small sample, then the F version is preferable, right? So the chi-squared version, at times they can also call it LM test. What's the meaning of LM? LM. LM. Lagrange multiplier. You never heard of this word before? LM. Okay, no problem. You can find out. So LM means Lagrange multiplier. Does anybody have an idea of any LM test? You should know. You don't know any LM test? Really? Autocorrelation, where we were testing for autocorrelation last semester.
We said LM, we didn't say that.
You remember the Bush-Godfrey test, BG test? It's an LM test. You forgot. Okay. What's this? ROSS?
Residual sum of squares.
Residual sum of squares, right? Okay. I will tell you something briefly about this residual sum of squares. Very briefly. Guys, we have total sum of squares, and then we have explained sum of squares, and we have residual sum of squares, right? So if you do an estimation, you have the explained part. The model is trying to explain what is happening to the dependent variable. That's the explained part. And you have the unexplained part, which is represented by error term, right? So what do you want? Do you want the explain sum of squares to be higher than the residual sum of squares, or vice versa? Which one do you prefer? Do you want a low residual sum of squares or a high residual sum of squares?
We want a high explained sum of squares.
And what
A
of
lower?
Low, yes. Because you know, the higher the explained sum of squares, the higher the explanatory power of the model. And you want a model which has a high explanatory power, right? Okay. So when you add up the explained part and the unexplained part, it gives you the total sum of squares. So what next? Okay, now we are going to look at the assumptions one after the other. What's this? So this is the first assumption. The expected value. Okay. The expected value of the error term should be 0. That is the mean value, right? It's very easy. You know, if you're trying to run a regression, it's very easy to allow this, that is to satisfy this assumption. The easiest way to satisfy this assumption, what's an idea? How can you satisfy this assumption? Because you know these assumptions must be satisfied. So how can you satisfy this assumption? The expected term, the expected value of the error term should be 0. Nobody has an idea? Okay. This assumption can be satisfied by including a constant in the model. So for instance, if we are trying to investigate the determinants of GDP, let's say financial development, one, financial development, whatever. Okay, so let's assume that we are trying to find out the impact of financial development and population on GDP. So just by including a constant in this model, we satisfy that assumption. We ensure that the expected value of the residuals is 0, right? By the way, you understood? Who didn't understand? Who understood what I wrote? Sorry?
You watched the video anyway.
Okay.
So if you say you don't understand, you don't understand.
For all the necessities, we cannot update.
Yes, I'm gonna stop the recording now.
Next, assumption number 2. Variance should be constant. If the variance is not constant, how do we call it? Heteroscedasticity. If the variance is constant, it is homoscedasticity. Okay. Looking at this graph, what do you think? Is the variance constant?
No. It's a heteroscedasticity.
This graph, by the way, these data points are residuals. So yeah, they say if we plot the residuals, let's say you calculate the residuals and you plot on a graph. So from this graph, is it constant? What do you think? The variance.
The variance are constant. Oh, yeah.
Sorry?
The variance here in the it's like, I'm not sure. I'm confused.
Who is sure? Hello, you are very quiet behind there. What do you think? Yes, you. I've never heard you speaking. Never. You always you just sit behind and you're always quiet. Then you don't speak. Why? Okay. Ikra, what do you think? What do you think? Oh, you don't even know the question. Okay.
Means in the middle is equals square to both sides, up and down.
Yes. Yes.
Those are residuals, like this is the regression. That's
Okay, you don't even know the question. Okay. Those who don't know the question, I'm not going to repeat the question. It's your punishment. So it means you were not following up. How do you expect to answer a question you don't even know?
If it's an equal spread, if they're possible, we need to know, right?
I would say that it's a heteroscedasticity. I would say that it's
Yes. Literature, geography teacher, what do you think? She doesn't even know the question.
I don't know the answer. I forgot.
What's the question? What's the question?
Sure.
What is she saying? Oh, no. What's the question? Okay, no problem. I'm not going to tell you. We are going to continue. How to detect.
It
Is what?
is.
Okay, guys, let's try to be fast. We have no time. Now, we are going to focus. We are going to focus on heteroskedasticity, autocorrelation, normality, and multicollinearity. You know, we always focus on these 4 things. But it doesn't mean these are the only 4 assumptions, right? You know, as you rightly said, there are 11, 10 plus 1 assumptions. Okay. So how to detect heteroskedasticity? You should know on e-views, right? What do we do? On e-views, how do we detect heteroskedasticity? We have 5 tests on e-views, 5. Really? What do you mean by do I expect you to remember? I know at least 8 different tests. If you wake me up from bed, I'll tell you. So you should know.
White test,
Yes.
correct? The answer is correct, white test.
Is that all you can remember?
No, I can remember others on kind of.
Yes, continue. White.
That's the best one, though. That's the best one.
Yeah, it's easy because it's white. Of course, everybody remembers white.
No, I will tell you.
Everybody remembers white. So you most probably.
Subject of age.
Okay. So,
Yeah.
okay, guys, on e-views we have white tests.
Even you start with
The reason,
white.
the reason why I start with white is the general test. Of all these 5 tests we have on e-views, the white test is the general test, right? Of course, we have the Glacier test, we have the Harvard test, we have the BPG test, and there are others. So I'm not going to talk about these tests we don't have on e-views. For instance, you see this one, the Gottfeld quant test. We can also use it to test for the presence of heteroskedasticity. But this test is not on e-views, so I'm not going to talk about it. But just know it, that we have this test. By the way, using this test we have on e-views, we can use this test to formally test for heteroskedasticity statistically. But informally, we can always check the graphs, right? So here, graphical methods. Okay, on Friday, on Friday we'll do tutorials and we'll talk about these assumptions. I will show you how to use the graphs to check. But you know, the graphs gives you a hint, it gives you an idea, but you have to formally test for using a statistical test.
We don't know what is one. We are looking the graph, but we don't say if the heteroskedasticity or not.
No, if you look at the graph and from the graph you see that the variance is constant, then you can say it's giving you some hints that there is homoskedasticity, but you still have to formally test for it using statistical tests. You know, we have 5 tests on e-view, so there's no harm in doing this test. Okay, we are skipping this GQ test. I'm skipping it, by the way. Okay, now we have white tests. This is the general test for heteroskedasticity, right? So white general test is one of the best. Okay, you see, it's one of the best methods, and it is the general test. So the test is carried out as follows. Assume that the regression we carried out is as follows. So let's say this is the regression. Of course, we know this is dependent variable y. You know, this is our constant. These are regressors and their coefficients, and this is error term. You know all of this, right? This is a typical regression model. And we want to test this. We are trying to test if the variance of the errors, these errors, is constant. We estimate the model obtaining the residuals. So you estimate this model, right? And you will get the residuals. These are the residuals. By the way, when you see a small cap above, it means sample, right? Because you know we have sample and population. So you estimate this regression and get the residuals. Next, run this auxiliary regression. So what do I mean? Once you obtain the residuals from the first step, use these residuals as dependent variable in the new regression, auxiliary regression. And what are the regressors you're going to use? If you see here x2, we are still using x2 here, right? If you see here x3, we are still using x3 here, right? If you see here x2 squared, so we are squaring this x2. If you see here x3 squared, we are squaring this x3. And if you see here x2 times x3, so we are finding the product of both of them. And we have v here, which is the new error term of this auxiliary regression. So what does it tell you about the y test? So of course you don't do this manually. eViews is doing it for you, but this is what eViews is doing, right? So in the first step, eViews runs the regression, obtains the residuals from that regression, and uses these residuals as dependent variable in the second regression. Then the independent variables in the second regression are the same independent variables you have in the first regression, plus their squared values and the product between them. So you square this, and then you find the product. Understood? Okay. Now, this is the second step, auxiliary regression. When you go to the third step, obtain R, by the way, you know what R squared is, right? Coefficient of determination. Obtain R squared from the auxiliary regression and multiply it by the number of observations. So when you run this auxiliary regression, it's a normal regression, right? You will see the R squared. Get the R squared, of course, you know the number of observations in whatever you're doing. Get the R squared and multiply it by T. You know T is a number of hold on. Okay, yes. Obtain R squared and multiply it by T. T is a number of observations. So you see here, T times R squared. So you're just multiplying the number of observations by the coefficient of determination. And this follows a chi-squared distribution, right? So here they say where M is the number of regressors in the auxiliary regression. So here, in this auxiliary regression, the number of regressors is represented by M. Now, in the fourth step, if the chi-squared test statistic from this step, the test statistic, is greater than the corresponding value from the statistical table, then reject the null hypothesis that the disturbances are homoscedastic. Guys, this is typical hypothesis testing. Of course, you know that, as we mentioned in the tutorial last week, if the test statistic is greater than critical value, then we reject null hypothesis, right? Okay. So after doing this, we have our test statistic, which in this case is chi-squared statistic. We are comparing it with critical value. So therefore, we will look at the critical value from the tables of the chi-squared distribution. And if that test statistic is greater than this critical value, then we have to reject the null. Of course, you know, if it is less than, if the test statistic is less than critical value, then we fail to reject the null. And what is the null hypothesis in this case? The disturbances are homoscedastic. That's the null hypothesis. So if you reject this null and you accept the alternative, it means there is heteroscedasticity, right? But if you fail to reject the null, it means there is no heteroscedasticity. So typically, this is what if use is doing. Everything I've explained here, you don't have to do it manually, but that is how if use is performing the White's test. Okay. Consequences of using ordinary least squares in the presence of heteroscedasticity. What's the meaning of this? Of course, you know we should not use ordinary least squares if these assumptions are not all valid, right? But then some people might want to still use ordinary least squares even though these assumptions are not satisfied, but there are consequences. So what is the consequence? What are the consequences if we are using ordinary least squares? So it is written here. Ordinary least squares estimation still gives unbiased coefficient estimates, but they are no longer blue. So, okay, if you use ordinary least squares, they will still be unbiased, but they will no longer be blue. Why? Who can tell me why?
Because it's unbiased, like they have fulfilled the whole.
You know, part of blue is unbiasedness. Blue means best linear unbiased estimator. So it is still unbiased, which means the U part is satisfied, right? So what is making it no longer best?
Because it's not the best variance. So
Sorry?
It's not the minimum variance from the.
Yes, because it no longer has the minimum variance in the class of all unbiased estimators. Yes. This implies that if we still use ordinary least squares in the presence of heteroscedasticity, our standard errors could be inappropriate, and hence any inferences we make could be misleading. Who can explain this statement? What does this statement mean? Who can help me? If we still use ordinary least squares in the presence of heteroscedasticity, our standard errors will be inappropriate, and any inferences we make will be misleading.
So basically,
yes,
our standard errors and like disturbances, U-turn, are not the best. Then we would be using, let's say, one with a high variance. That can lead to a sort of conclusion that we shouldn't have used the best one.
Okay.
The model is not correct. You should change our model.
You're funny at times.
Sometimes it's not the model. Sometimes.
Okay, guys, I'll tell you something. Do you know how to calculate T statistic or T ratio? T, you know? T statistic or T ratio. Of course, you know, on if use, we are going to directly have the T statistic, right? But how do we get this T statistic? Whenever you estimate a model on EViews, if you check the regression output, you get the coefficient, you get the standard error, you get the T statistic, and you get the probability value, correct? Okay. If we want to get the T statistic, we simply divide the coefficient by standard error, right? So just simply take the that coefficient divided by, it's like you guys are not understanding what I'm saying. I will show you something, give me a second. As I can remember, I sent something on. Okay. Can I open this directly? Why is it not opening? I think I should download it. It's not coming.
This is one of the consequences of using
okay. This is.
Changing variable is not changing the model. When one variable is changed, the model is not the same. You change the model.
Okay, I didn't say no. Did I say no? I didn't say no. Did I say no? Is that why you went outside?
No, where's my end?
Okay. I thought maybe you got angry and you wanted to leave. Okay, guys, this is a typical regression output, right? So if you estimate any model, a regression, you have the coefficient, you have the standard error, t-statistic, and probability value, right? How do you calculate this t-statistic? Simply take this coefficient and divide by the standard error. You can try. Choose any coefficient here and divide by its corresponding standard error. It will give you the t-statistic. That's how we calculate the t-statistic. And yes, you can try if you have time. And we use this t-statistic and these probability values to do hypothesis testing, correct? Why are we doing hypothesis testing? Because we want to make inferences about the true population from the sample, right? We don't have the population with us. We have just the sample. But we are carrying out a study because we want to do policy implications. We want to make inferences about the population. So if we have our results about a sample, in order for us to generalize these results of our sample to the population, we need to do hypothesis testing. We use t-statistic to do hypothesis testing. How do we calculate t-statistic? Coefficient divided by standard error. Okay. Now, if standard error is wrong, it means our t-statistic will be wrong, right? If t-statistic is wrong, it means hypothesis test will be invalid, and any inferences we make would be invalid, it will be wrong. So that is what this statement is telling us, that our standard errors will be wrong, and any inferences we make will be misleading. Understood? Okay. Whether the standard errors calculated using the formulae are big or small will depend, whatever. They can be big or small, but know that they will be wrong. So please don't use ordinary least squares in the presence of heteroscedasticity. How do we deal with heteroscedasticity? That is solution. How can we solve heteroscedasticity problem? Yes.
First, if the data is not in log form, you can convert it into log form.
Okay. Sure. Okay. Yes, that's correct.
That's
Okay.
thing.
Yes. Actually, you know, it's always advisable to always use log transformation because it tries to solve so many problems. Normality problems, heteroscedasticity, even autocorrelation. But please, it doesn't solve stationarity problems. I know you don't know what stationarity is, but when we'll start doing stationarity. So because I said log transformation solves many problems, don't think it solves stationarity problems. It does not. Okay. So with heteroscedasticity, log transformation is always an option. It can try to help. Also, we might know the nature of the problem, and we might not know the nature of the problem. So if we know the nature of the problem, you want to say something? If we know the nature of the problem, what can we do? That if we know the kind of heteroscedasticity, what can we do? We can use a method they call generalized least squares. You have an idea? GLS, generalized least squares. We can use it, but that's if we know the nature of the problem. But typically, it's almost impossible to know the nature of the problem, right? So in that case, we can use White's correction method. You remember Uber White? Yeah. You know, there is a guy called White. I don't know his other name, but I'm sure Robert. Maybe Robert White. I forgot his other name. You can search it. Just Robert White. I'm sure that's or maybe that. Okay, Herbert White, not Robert, Herbert, whatever, it doesn't matter. So this guy, he has many econometric contributions, but he has two key contributions he made in econometrics, which are related to heteroskedasticity. First, he provided us with a method we can use to detect heteroskedasticity, which is the white test, and it is the general test. And then he also told us that, okay, if we detect heteroskedasticity, we can try to solve it using this method. So he provided a detection method and correction method. Detection and correction, right? So his detection method is the white test we know from e-views, and his correction method is also the white correction method you know, robust standard errors. So in his correction method, try to apply robust standard errors. And if you look in e-views, you will see there Uber white, something like that. White heteroskedasticity consistent standard errors. So these are actually different names of the same thing, right? So it is White's heteroskedasticity consistent standard errors. That's the method he's using. In e-views, you will see Uber white. Actually, it is robust standard errors. Okay. You know all these things from Bank 504. So yeah, if the form of the heteroskedasticity is known, then we can use generalized least squares, I mentioned already. And a simple illustration of generalized least squares is as follows. So this is what is happening with it. But typically, it is difficult for us to know the form of the heteroskedasticity. So in practice, we don't use this method. In practice. Theoretically, they're telling us that we can use it if you know the form of the heteroskedasticity. But it's not possible, it's not that easy to know it. So in practice, we don't use GLS. So we have other solutions. Of course, you can always transform the variables. You can do log transformation, as we mentioned. You can use White's heteroskedasticity consistent standard errors, I just mentioned, which is actually the robust standard errors. And the effect of using White's correction, okay, it's trying to tell you what will happen if you use this method, but we can use this method. There is another method we can use. Who remembers? Who remembers? You forgot? Newell's method. What was this method telling us? This method is heteros. I don't like spelling this thing. It's too long. Skedasticity and autocorrelation consistent standard errors. What's the meaning of that? This Newell's method is heteroskedasticity and autocorrelation consistent standard errors. That's what is happening there. Huber white is just heteroskedasticity consistent standard errors. So this Newell's method is trying to solve both heteroskedasticity and autocorrelation problems at once, right? So if you have a situation where you are faced with both problems, you have both heteroskedasticity and autocorrelation problems, you can use this method. It's trying to solve both of them at once. But with the Huber-White method, it's solving just heteroskedasticity problem alone. Okay. From last semester, you know these things anyway. What next? Okay, the concept of lagged value. Lagged value. Have you ever heard of lagged value? What is lagged value? There is a difference between, okay, I'll tell you something interesting. Lagged value and, I should take off this. Lagged value and phase difference. We'll see more of this most in the weeks ahead. But let me try to explain what is happening. Okay, let's say we have a time series. This is a time series, right? From the 9th month of 1989 till the 4th month of 1990. And we have these values. So in September 1989, we have 0.8. In October, we have 1.3. And right up till the end of the period. So these are our values, YT. Now, guys, look at this subscript here. It is YT. Here you see what's the subscript? It is YT minus 1. T minus 1 means it is lacked 1 period, right? If they put there T minus 2, it means lacked 2 periods. T minus 3 means lacked 3 periods, whatever. So T minus something, T minus I is lacked value. And that I would determine the number of periods. Okay. So if it is lacked 1 period, you lose 1 value, right? If it is lacked 2 periods, you lose 2 values. If it is lacked 3 periods, you lose values. So what is happening with the lacked values? These are the lacked values. Are you seeing here that this first value here is actually the second value here, or let's say the first value here, but we have lost 1 value. So we lose 1 value, and this first guy here comes down. So eventually we will lose the last value, right? Because if this guy here, who is number 2, comes here, comes down, and eventually we will lose this last value. Do you understand? So that's lagged value. It simply means 1 period behind. Yes, periods behind.
1.3.
So if it is lacked 1 period, it means you lose 1 value. If it is lacked 2 periods, you lose 2 values. If here was y minus 2, then we will lose this value and this value. And this 0.8 would have been where this 1.3 is, which means we would have eventually lost these last 2 values, 0.1 and 0.0. Ikra, you look confused. Are you now fasting? You started fasting? You should start. It's getting late, you know. Okay, guys, what is this? Change in YT. What is that? This change symbol is difference operator. Difference. Okay, this is difference. Difference operator. So it's actually the first difference. So this change in YT simply means the first difference, right? And how do we get the first difference? It is actually YT minus 1. So if you see, YT minus 1 gives you the first difference, right? It looks strange to you, but I can assure you it's very easy. When we will start talking about a unit good test, you will understand the concept of first difference, right? So don't look at it as if it is difficult. By the way, you are not even supposed to, you will not be expected to do these calculations manually if use is directly calculating it for you. But at least I'm trying to explain what's happening in there. So key takeaways from here. YT minus I, that I can be 1 or 2 or whatever, but T minus something is lacked value. If it is T minus 1, it is lacked 1 period. If it is T minus 2, it is lacked 2 periods. T minus N, lacked N periods. Change in YT, that change symbol is the difference operator. So it's telling us that this is first difference, right? And to get the first difference is simply YT minus 1. Okay. Autocorrelation. What's autocorrelation? We talked about heteroscedasticity. What's autocorrelation?
The correlation.
Yeah, autocorrelation is okay. By the way, guys, you know what is correlation, right? Correlation metrics, you know what is correlation. What's correlation metrics? It's showing us linear relationship. right? Okay. So why the word auto? Why did they put the word auto? Automatic. Are you sure? That's perfectly wrong.
That was funny.
It's perfectly wrong. Not automatic. Okay, why did you not say automation? Why did you choose automatic? You would have said automation because there are many autos. Okay, so this auto here is because it is correlation with itself. You know, when we are talking about correlation, like correlation metrics, we are trying to look at correlation between two variables. Correlation metrics is telling us what's the correlation between GDP and FDI. Is it positive? Is it negative? Is it strong, weak, medium, right? And if both of them are regressors, we can talk about multicollinearity. Okay. So it is correlation matrix is telling us linear relationship between two variables, U and I. But if it is correlation between the same thing, like the same variable, then we use auto. So autocorrelation, we're actually talking about correlation between two or more error terms. It's the same variable, error terms. So it's autocorrelation. Okay. Now, we don't want autocorrelation. We don't want error terms to have this linear relationship, right? So we want the covariance between one error term, ui, and another error term, uj, to be 0. Covariance between error terms should be 0. Of course, I should be different from j, so you should not take two the same error terms. It should be different. Okay. Obviously, we never have the actual use, so we don't have the population, so we are trying to use sample. So how can we detect autocorrelation? How can we detect autocorrelation? Guys, please, everything seems very boring. I can see from your faces, but what I want to tell you is that for each of these things, try to know 4 things. Try to know how to detect it. I can remember I sent you a document last semester, a document here. Try to know how to detect it. That is how to test for it. Number 2, try to know what causes it. Number 3, what are the consequences if we use ordinary least squares in the presence of this problem? What happens? What is the consequence? And number 4, how can we solve the problem? Right? So we already talked about these kind of things for heteroscedasticity. Now with autocorrelation, how can we detect autocorrelation? That's the first thing. Of course, the graphs can help. We can check the graphs. It can help. Secondly, we have some statistical tests. We have, what tests do we have? 2. Yes, I'm asking you because you know. You know, we have 2 tests I mentioned to you last semester, how we can detect autocorrelation. You forgot everything. You forgot? And you're happy?
No, I'm not happy. If I look at it, I remember, but it's not different.
Of course, Dublin Watson. You forgot, she did not forget.
Because it doesn't talk anymore.
Dublin Watson test, we can use the Dublin Watson test to test for autocorrelation, right? You know the Dublin Watson test statistic ranges between 0 and 4. If it is around 2, it means there is no autocorrelation. But if it is far from 2, that is closer to 4 or closer to 0, it means we have autocorrelation, right? And we also have, sorry? No, it should be around 2 for it to be that there is no autocorrelation. But if it is far from 2, that is closer to 4 or closer to 0, because it ranges between 0 and 4, then it means we have autocorrelation. We also have the Lagrange multiplier test, Bush-Godfrey, LM test, right? Statistical test we can do on issues. Okay, guys, this Bush-Godfrey test is better than Dublin-Watson test. Dublin-Watson test has some problems. First of all, what I'll tell you is, in the Dublin-Watson test, we have okay, you cannot just say if it is closer to 0, there's autocorrelation. If it is closer to 2, there is no autocorrelation. But we have a zone of indecision. I think I should show you. So of course, you can check the graphs. The graphs gives you a hint. You can check the graphs. Okay, I will show you something I'm trying to talk about the Watson test. You will see there is a zone of indecision where we cannot make a decision. Before we get there, so this is how the Watson test statistic is calculated. The test statistic, why are you packing your bags? I'll close that door, you're not going to anywhere. The test statistic you see on eViews, right? This is how it is calculated. Nobody expects you to cram this formula because you are not doing this thing manually. eViews is doing it for you, and you just need to know how to interpret it, right? Okay. I didn't say so. Don't quote me anywhere, sorry. You should memorize this formula because most probably, I don't know. The Debye-Watson test is a test of first-order autocorrelation. So this is also one of the limitations of this Debye-Watson test, right? It tests autocorrelation only at first order. So if the order is more than 1, we cannot use this test. Okay. Sorry? No. You are not going. No. I refused. Look at something. Debye-Watson has 2 critical values, upper critical value and lower critical value. And there is an intermediate region where we cannot reject. So we have a zone of indecision. I'm going to explain to you what that means. Okay. You remember this? If Debye-Watson is closer to 2, it means there is no autocorrelation, right? But if it is far from 2, problem. But it ranges between 0 and 4. Okay. By the way, this is it. It ranges between 0 and 4, right? And it should be closer to 2. Okay. But there is a problem with this test, as I was trying to explain. Now look at, it ranges from 0. By the way, you can go if you want. You can go if you want. Yeah. It's, I will stop recording immediately you leave. So, Debye-Watson test statistic ranges from 0 to 4, right? Now, look at this DL is the lower critical value, right? And we have upper DU, something like that. Okay, look at if it falls around here. Of course, if it is around 2, look at something. If the test statistic, if the value falls around 2, it means there is no evidence of autocorrelation, right? So we cannot reject. The null hypothesis here is that there is no evidence of autocorrelation. We cannot reject this null hypothesis. There's no autocorrelation, that's the meaning, if it is around 2. Okay, if it is around 4, around 2 means closer to 2. Closer to 2. If, sorry guys, if it is far from 2 but close to 4, how far? Okay, now between 2 and 4, if it falls in this region, yeah, it means we can reject. But if it falls in this region, it means it is inconclusive. We cannot say if there is actually negative autocorrelation or not. If we have enough evidence, it's inconclusive. Same thing here. If it's around 2, it means there is no autocorrelation. If it is really close to 0, it means positive autocorrelation. But if it falls in this zone, it's inconclusive. So because of these zones of inconclusion, it makes our life difficult. Trying to use this Debye-Watson test, and also it tests autocorrelation only at first order, right? So because of this kind of things, there are some problems with the test. We prefer the Lagrange multiplier test. Okay. Which this is it, the Bush-Godfrey test. Sorry? Okay, I'll tell you. Can you see DU means upper critical value, DL means lower critical value? Yes, these values, correct. Okay, so guys, another test we have for autocorrelation is the Bush-Godfrey test, the BG test. Is actually an LM test, Lagrange multiplier test. This is a better test than Debye-Watson test, and it's actually the general test for autocorrelation, as far as I know. It is a it's a more general test. Why? Because it tests autocorrelation at any order. Remember, Debye-Watson will test autocorrelation only at first order, order 1. But if we have second order, third order, fourth order, nth order, we cannot use Debye-Watson. So this test is better because it can test autocorrelation at more than 1 if the order is more than 1, right? And for this test, of course, you know how to perform this test on EVIF, right? You just punch the button and you get the results, and you know what the null hypothesis is. Where are you going to? Are you trying to escape? Okay. I thought you were going to pray. It's fasting time. Going to pray. You're not fasting today, but you fast on other days. Try to fast. Try to fast. You know, you are a Muslim, so it's important. Okay, guys, so just have it in mind that the Bush-Godfrey test is a better test than the Debye-Watson test, right? And I gave you 2 important disadvantages of the Debye-Watson test. It tests autocorrelation only at order 1, and we have this zone of indecisions. With the BG test, we don't face these problems, and it can test autocorrelation at more than, if the order is more than 1. Okay. Now, what are the consequences of ignoring autocorrelation? What happens if we use ordinary least squares in the presence of autocorrelation?
Might be not the best.
The coefficients are still unbiased, same with heteroscedasticity, they are still unbiased, but again, they are not best, which means they are not efficient, which means they no longer have the minimum variance in the class of all linear unbiased estimators. Therefore, they are no longer blue. Even if you increase the sample size, right? You know, you can try to increase the sample size. It might make it consistent, but it is no longer efficient. It does not have the minimum variance. Therefore, if standard error estimates are inappropriate, there exists the possibility that we could make wrong inferences. I already explained this statement previously, right? Because, you know, in order to make inferences, we do hypothesis testing. We use t-statistics to do hypothesis tests. And to calculate t-statistics, we are dividing coefficient by standard errors. So if standard error is wrong, it means t-ratio will be wrong. Therefore, hypothesis testing will be invalid. And any inferences we make will be misleading. Okay. R squared is likely to be inflated relative to its correct value. So this is another consequence. We might have a high R squared, which is not actually telling us that there is a high explanatory power. It's just because we have autocorrelation. Okay. How can we solve autocorrelation? By the way, remedies means solution, right? Okay. Of course, we always have our log transformation, which always helps. So it's always good to do log transformation because it tries to solve these kind of problems. Again, if we know the nature of the autocorrelation, we can use generalized least squares, but this method is not practically possible because it's difficult for us to know the nature of the problem. So we can try to solve it with the Neuer-West method I told you about, which is trying to solve both heteroscedasticity and autocorrelation simultaneously. let's read what is written here. Okay, if the form of the autocorrelation is known, we could use generalized least squares, of course. But then in practice, we almost never use this method because it's difficult to know the form of the autocorrelation. But such procedures are correct for autocorrelation require assumptions about the form, whatever. If these assumptions are invalid, the cure could be more dangerous. So what they're trying to explain here is that before we use generalized least squares, we need to make some assumptions. But if we make these assumptions wrongly, then instead of trying to solve the problem, we'll instead create a bigger problem. That's why they say the cure will be more dangerous than the disease, right? However, it is unlikely to be the case that the form of autocorrelation is known. So, since in practice we cannot know the form of the autocorrelation, so we cannot use generalized least squares in practice, right? So there are other methods we can use, which I just mentioned. Dynamic models. Is this too important? Let me see. All the models we have considered so far have been static, but we can easily extend this analysis to. Okay, we are trying, for instance, this is a static model, and this is a dynamic model. Look at both of them. What's the difference? Looking at this model and this model, who can tell me the difference? The difference is clear, but who can tell me the difference? Then I'll explain why one is static and the other one is dynamic. Nobody saw anything? Okay. Look at yt here depends on xt, x2t, and xkt, right? So y depends on x, static model. But in this dynamic model, y depends on x. It depends also on y. So it depends on its own lag value, right? So we include lag values of the dependent variable as part of the regressors. So it's dynamic, trying to make it more complex. And we could extend the model even further by adding extra lags. So these kind of things. Why might we want to include lags in a regression? Okay, I will just tell you something about these lags, something which I feel is important about these lags, because here they are saying, why might we want or need to include lags in a regression? Of course, you know, in a regression model, we can have y as dependent variable and x as independent. So y depends on x, right? But if we include lagged values of the dependent variable as part of the regressors, it means y depends on previous y. Like nobody's understand what I'm saying. Look at here. Y depends on x, right? X. So GDP depends on FDI, for instance. We are trying to estimate the determinants of GDP. So we have other variables, FDI, population, whatever. But if we are trying to find out what is happening to GDP, then why should we include lag values of GDP? Why should GDP depend on GDP, previous value of GDP? Any idea? So why should we use lag values of a variable? Why should a variable depend on its own lag values? Okay. Yes. So typically we can use these kind of things for forecasting. If we are trying to forecast the future, right? Because you know, the best way to predict the future is by looking at the past. So if a variable depends on previous values of that same variable. You can use previous values of a variable to predict future value, right? So by including lag values of a particular variable, we can forecast, we can do forecasting. So as far as I know, that's one, I don't know if it's mentioned here. Okay. Models in first difference form. We saw it before, right? We saw YT and we saw YT minus 1. Guys, these things look boring, I know. I can see from your faces. We have YT and we have YT minus 1. This YT is the current value of Y, right? Current value. T, that T there simply means time period. So this YT is the current value of Y. We can say it is the current realization of Y, right? So here, let's say YT minus I. This YT minus I is lagged value of Y. This I can be any number. It can be 1. If it is 1, it means lag 1 period. If it is 2, it means lag 2 period. I just put I. Okay. Now, if I take YT minus YT minus 1, it gives me first difference of YT. You know, the difference operator. So to get the first difference of a variable, take its current realization minus its lagged value, lagged 1 period. Okay. Now, this first difference is very important. It might not be, by the way, first differencing is also some kind of transformation. Of course, you know, we have log transformation. We also have difference transformation. So by taking the first difference of the variable is some kind of transformation, right? This first difference is very important. When we'll be seeing unit root tests, you just keep it in mind. First difference is very important. You will discover that we have, let me just, it's an aside, but I'll mention it. We have level form and we have first difference. Right? So we'll try to check if a variable is stationary or it is not stationary. We'll check its stationarity at its level form, and we'll also check its stationarity at first difference. But know that first difference is current realization minus lag value. You don't have to do this if this is doing it for you. But we'll check stationarity of a variable at level form and at first difference. And depending on the results we'll have, we'll make a decision. For instance, just for your information, if a variable is stationary at level form, then we say it is I0. I mentioned it here, which means it is integrated of order 0. But we can have a situation where a variable is non-stationary at level form, but stationary at first difference. In that case, we'll say it's integrated of order 1, which means it is I1. So that's just to tell you how important first difference can be. We'll see it when time comes. Models in first difference. Another way to deal with problem of autocorrelation is to switch to first differences. Okay, this might be another solution. So if you try different solutions and it does not work, then you can try to do difference transformation. You can try to switch to first differences, try to solve autocorrelation problem. The first difference, so are you seeing what's happening here? Is the current realization minus the lagged value to get the first difference, and this is the first difference. That triangle is the difference operator. Okay, so that's what is happening in there. By the way, how do you know that this model is in first difference? You see the difference operator. This is difference operator. And we have difference operator. Here we have our difference operator. So these models are in first differences, right? Long run static equilibrium solution. Okay, this is another solution for autocorrelation, but in practice, how practical is this? I'm not too sure this is too practical. We cannot do it. I've never done this on EViews anyway. Guys, you can read this, try to understand what this is trying to say, but I'm not too interested in this long run static equilibrium things. I can skip it. All these lag values. Okay, we can talk about multicollinearity. So again, I'm insisting for autocorrelation and heteroscedasticity, 4 important things you should know. How to test, detect the problem, what is the cause of the problem, practical implications, what happens if we persist to use ordinary least squares in the presence of this problem, and number 4, how to detect or how to solve or remedy this problem. Those 4 things are very important. I remember in your exam, final exam last semester, Migahuja asked it. Most probably in your midterm exam, you will still see these kind of things. For each of these problems, know these 4 things. It's very important. I remember I sent you a document. It can help. We also have multicollinearity. By the way, what's multicollinearity?
The relationship between the independent variables with the residual variable.
No.
No?
When the independent variables are...
Yes, if the independent variables are related to each other, if they have a powerful linear relationship. See, please, I'll mention something to you. Autocorrelation, normality, heteroscedasticity, these 3 problems, think about the residuals. Of course, we have normality in the data. If you check descriptive statistics, Jagbera test, you have normality in the data. But when we are talking of diagnostics, we focus on residuals. So we talk of normality in residuals, not data. So for normality, autocorrelation, heteroscedasticity, think only about the residuals. For multicollinearity, think only about the regressors. Forget about any other thing. That's why if we are checking correlation metrics to try to detect multicollinearity, we don't care what is happening between the regressor and the regressant, that is dependent variable. We are checking only the relationship between the regressors. If it is powerful, like above 80–90%, really powerful, then we have hint of multicollinearity. So of course, we want a strong relationship between the regressor and the regressant, because it means that the model has a high explanatory power. But we don't want a strong relationship between the regressors. Why? Because you know, if these regressors are very related to each other, then it is difficult to hold one constant while interpreting the other. Because you know, partial regression coefficients, if you want to interpret the effect of one regressor on the regressant, you have to hold the others constant. But if they are too related to each other, then it is difficult to have the pure effect. So we don't want multicollinearity problem. Okay, so with multicollinearity problem, how can we detect it? So I'll talk about these 4 things. First, how can we detect multicollinearity? Correlation metrics. Okay, before correlation metrics, there are some hints you can check. First of all, look at your regression output. Look at the coefficients. Look at the R squared. Look at the F statistic. If the R squared is very high, if the F statistic is significant, and most of your coefficients are insignificant, and maybe the signs of the coefficients are not logical, then it gives you some hint of multicollinearity, right? Because you have a high R squared, your F statistic is significant, but most of your T statistics are insignificant, and your signs are not logical. What do I mean by signs are not logical? Okay, let me ask you a question. Intuitively, what do you think can be the impact of financial development on economic growth?
Positive relationship.
Positive or negative? Like if you are trying to investigate the impact of financial development on economic growth, what do you expect? You expect positive relationship, right? And you can explain it. If you have negative relationship, can you explain it?
No, unless there's from people.
It doesn't look logical. So if you do this estimation and you see that the coefficient of financial development is negative, it's not logical. You understand? So if your coefficients are not logical, many of them are not logical, most of your T statistics are insignificant, but you have a high arrow square, then it gives you some hint of multicollinearity. But then you have to formally test for it. So to formally test for multicollinearity, we can use a correlation matrix, of course, but we are checking just between the regressors. There should be no powerful relationship that is above 80, 85, 90, right? If it is really high, it means there's multicollinearity. We can also check variance inflation factors. We'll see in the tutorials. And you know, with variance inflation factor, before checking it on e-views, you must first of all estimate the regression, right? You estimate the regression, then you can try to check it. I'll show you. With a VIF, what's the rule of thumb? Your VIF should not be high. It should not be more than 10. In some sources, you see they are even more conservative. They will tell you that it should not be more than 5. But I think that's for me, and I was also taught that it should not be more than 10. So if your variance inflation factor is really high, more than 10, it gives you a hint of multicollinearity. You know, the reverse, like the reciprocal of variance inflation factor is what we call tolerance factor. So if you take 1 over VIF, it gives you tolerance factor. If you take 1 over tolerance factor, it gives you variance inflation factor. So both of them are reciprocals of each other. So what does it mean? It means we don't want a high VIF and we don't want a low tolerance factor. So if your tolerance factor is close to 0, it means multicollinearity. If your VIF is very, very far, really high, it means multicollinearity, right? So we want tolerance factor to be high. It should not be more close to 0. And we want VIF not to be high. So we can check these kind of things. But if you ask me, I will say, you know, at times you can get conflicting results. Maybe correlation matrix is telling you that there is multicollinearity. VIF is telling you that there is no multicollinearity. So what should you do? Correlation matrix is a better test than VIF, I can assure you. So if you have conflicting results between both of them, then try to lean on the side of correlation matrix. We also have auxiliary regression. I'm not sure I showed you last semester, did I? I forgot. Maybe I might show you in practicals. We can also do some auxiliary regressions, and we can manually calculate these tolerance factors. I don't know if I showed you, I forgot. So these kind of things are important. Now with multicollinearity, so I've talked about how to detect it, right? Okay. Next, what causes multicollinearity? Let's talk about the cause. Multicollinearity. What can cause multicollinearity? Multicollinearity can be caused if you use variables which are very close to each other, variables which are very similar. For instance, let's say you're trying to investigate the impact on expenditure, like what determines my expenditure, and you're trying to use variables like my income and my wealth. What's it? Income and wealth are almost the same variables, so most probably you will find multicollinearity, that these variables are related to each other. So if you are using regressors which are very similar in meaning, most probably you might have multicollinearity. Okay, with multicollinearity, we have like 2 types. We have perfect MC and we have less than perfect MC, but very high. What do I mean by that? Okay, let's assume that 85% is our benchmark, right? In different sources, they will tell you different benchmarks. As I can remember, when I read Gujarati textbook, I saw that the benchmark was 80%. Then I remember Kohan Hoja told us his own benchmark is 85%, but Niga Hoja's own benchmark is, I think she told us 95%. So different sources tell you different benchmarks. But I think if you have, and again, just my personal opinion, if you have above 80%, you should be suspicious of multicollinearity. That's why it's always good to perform different tests, perform multiple tests, so that at least one can confirm the other. Maybe if you have above 80%, then you check various inflation factor and you see that it is really high, then you can conclude that there's multicollinearity, right? Okay, so let's take 80% as benchmark. We are checking the correlation matrix between two regressors, right? So let's say we have 88% and then we have 100%. So if the correlation coefficient, Pearson correlation coefficient between two of them is 100%, it means it is perfect multicollinearity. But we can also have like 88%, which is not perfect, but it is high, right? So we have two types of multicollinearity in this sense. Now, with perfect collinearity, E-views is not going to estimate it, I can assure you. So if you have two variables which are perfectly correlated, and you are trying to do the estimation, E-views will tell you error. It cannot estimate it. But if you have less than perfect, but very high, E-views will estimate it, but your standard errors will be wrong. That's why if you ask me, I will say perfect multicollinearity is better than less than perfect multicollinearity. Why? Because if it is perfect, then E-views is going to give you a warning that there is a problem, and so maybe you can check your data. But if it is less than perfect, E-views is not going to give you any warning, so you will do the estimation, then you have misleading results. Okay. Where are we? So, causes of multicollinearity, if we have variables which are very similar. Now, I just told you the consequences, right? So if we are trying to use ordinary least squares in the presence of multicollinearity, if it is perfect multicollinearity, we cannot even do the estimation. But if it is less than perfect, then we can do the estimation, but we'll have misleading standard errors. Hypothesis testing will be misleading. Now, consequences. How can we solve multicollinearity? Hello, Jam. How can we solve multicollinearity problem? Yes, so, yeah, sure. So if we have these variables which are related to each other, yeah, we can, first of all, we should try to use different proxies. Maybe you have a variable which theoretically is very important, it has to be there, so you cannot take it off. Try to use different proxies. It might solve the problem. Yes. If the worst comes to the worst, we can take away one or more of the problematic variables. But please, whenever you take away a variable from a model, always check if you have omitted variable bias, because maybe this variable is very important, so you have taken it out. You should always test. I showed you omitted variable bias last semester, right? Always test. If you test and it tells you that you have committed this problem, put back the variable and try to look for another solution. Okay. Also, we can do ratio transformation. For instance, let's say if GDP and population are two variables in our model, and we have multicollinearity, but you want to incorporate both variables, you can just take GDP over population and you use a different variable, GDP per capita. So this is ratio transformation. It can also help. Then, okay, so here problems if near multicollinearity is present, so R squared will be high. So guys, you can read these things. I give you a general overview. Correlation matrix, of course. So I think you can read these things. I just gave you an overview. So we have one more test which we did not see last semester, but we'll see this semester. Ramsey's reset test. This Ramsey's reset test is actually a portmanteau test. I don't know if I'm pronouncing it well. Portmanteau. This portmanteau means general. General. It's a portmanteau test. Why is it called like this? It's because the test, it's a test for many things. It can be used to test many different things. We can use it to test the functional form of a model. We can use it to test non-linearity. In fact, just know that it can be used to test more than one thing, right? So it's a general test. So when you see this word portmanteau, don't think that maybe portmanteau is a scientist who developed the test. No, portmanteau means general test. Okay. So this Ramsey's reset test, we'll do it in e-views. We are trying to see if the functional form is correct or not. What do I mean by functional form being correct or not? You know, in ordinary least squares, we are using linear models, right? For instance, if we have y equals constant plus beta 1 f di plus beta 2 population plus error term, whatever. Of course, this is dependent variable. This is constant, and we have our regressors and error term. Guys, this is a linear model. Why is it linear?
There is no power.
Because the power is 1, right? Okay. Now, we can have linearity. We can have two things related to linearity. We can have linear in the parameters, and we can also have linear in the variables, right? For instance, here, FDI is variable, but beta 1 here, coefficient is the parameter, right? So if we have a power here, more than 1, it means the parameter is not linear. But we can also have a power in the variable, right? But this is linear model because all powers are 1. But then, if we estimate this model and we have our results, we want to be sure if this model is correctly specified. Is the functional form correctly specified? Is it supposed to be a linear model? Maybe it's supposed to be quadratic model, non-linear. We don't know. Because I'll give you an example. There's something they call environmental Kuznets curve. I don't know anybody has ever heard about it. Environmental Kuznets curve. You heard about it? It's telling this environmental Kuznets curve hypothesis is telling us that there is a non-linear relationship, like actually an inverted U-shaped relationship between carbon dioxide and GDP, right? So if we are trying to find out what's happening to carbon dioxide emissions, then we can have here GDP, and we can also have here GDP. So we have GDP as a regressor, and we can also have a square of GDP, right? So you discover that this model is no longer linear. Why? Because we have power 2 here, right? So theoretically, maybe the theory is telling us that the relationship between carbon dioxide and GDP is non-linear. So we have to use non-linear model. So you can estimate a model. Maybe you made a mistake with the functional form. So you should try to check if the functional form is appropriate or not. We use the Ramsey reset test. We'll do it in e-view Zomboda on Friday, most probably. Inshallah. So,
Inshallah.
You know what inshallah means?
Why would I know what inshallah means? You think you're the only one who knows what inshallah means?
What, do you know what inshallah means?
Okay, keep asking me. Instead for you to be asking me what Ramsey reset test is, you're asking me what inshallah means. You think I don't know what inshallah means?
You mentioned it. It's like not a word we were speaking.
Okay. more surprises for you, you know.
So you want to know what it means?
I know what it means.
Okay, what
Why
does it
did you
mean?
say no?
I said I know. I didn't say no. I know what inshallah means. Inshallah.
Why did you?
Ah, I'll shock you.
Inshallah.
Okay, guys. So one criticism with the Ramsey reset test is that it is just telling us if the functional form is appropriate or not, right? Like for instance, in the Ramsey reset test, we'll see on EViews, what's a null hypothesis? The null hypothesis is telling us that functional form is appropriate. Alternative is telling us that not appropriate. Before I continue with this test, I'll tell you something about all these tests. I mentioned it last semester, but I'll repeat myself. Guys, generally in econometrics, of course, there are a few exceptions, but generally in econometrics, most at times, the null hypothesis is telling you that there is no problem, while the alternative hypothesis is telling you that there is problem. For instance, what is null hypothesis for heteroscedasticity test? It's telling you that there is no heteroscedasticity. Alternative hypothesis is telling you that there is heteroscedasticity.
There's a problem.
Yes. Autocorrelation, null hypothesis, there is autocorrelation. Sorry, there is no autocorrelation. Alternative hypothesis, there is autocorrelation. With normality, what's the null hypothesis?
Normally distributed.
Normally distributed. Alternative hypothesis, not normally distributed. With Ramsey reset test, null hypothesis, functional form is appropriate. Alternative, not appropriate. So most at times, the null is telling you that there is no problem, while the alternative is telling you that there is a problem. Of course, there are some exceptions like t-test, because you know with t-test, null is instead telling us that it is insignificant, which means problem, and the alternative is telling us that it is significant, which means no problem. So apart from t-test and f-test, with most of the other tests, null is saying no problem, alternative is saying problem. Okay. So we'll do the Ramsey reset test on EViews, and this is the hypothesis we are going to talk about. Actually, we are done. We have 5-10 minutes. So in 10 minutes time, you have 2 hours break. I give you 2 hours break. You're tired. Sorry. Okay, guys, normality. I'll talk about normality and we can close. So for normality, again, with descriptive statistics, we have normality of data, right? But here for diagnostic tests, we are talking about normality of residuals. And to perform normality tests, we are checking Jagbera tests, right? Of course, we can check the histogram. You know, in EViews, we check the histogram. It gives us an idea if it is normally distributed or not. But to formally test for it, we are using Jagbera test. Now, this Jagbera test brings 3 things together. It brings ketosis, skewness, and sample size. If your sample size is really, really, really big, then most probably your data and even your residuals will be normally distributed according to central limit theorem, right? Okay. Now, what is skewness? What is ketosis? With skewness, for normally distributed data, skewness should be 0. With ketosis, for normally distributed data, ketosis should be 3. We say it is mesoketic, normally distributed. But if ketosis is above 3, then it means we have excess positive ketosis, so it is leptoketic. If ketosis is below 3, it means we have excess negative ketosis, which means it is platyketic, right? Now, if skewness is 0, it means normally distributed. Sorry, 0 skew. But if skewness is 1, 2, positive skew. If it is -1, -2, negative skew. Guys, skewness is giving us an idea about the symmetry of the data points, the distribution, is it symmetrical or not? Why kurtosis is giving us an idea of the tails, like the peaks. If you check, I don't know if I can see it here. Okay, you see this is normal distribution, right? Why this one is skewed distribution? Skewed, are you seeing? This is normal distribution. Are you seeing that it is symmetric? Left side equals to right side. But here is not symmetric. Right side and left side are different. This is skewed. Okay. Yeah, look at this one. The blue line is normal distribution, mesochaetic. This black line is leptochaetic, which means kurtosis is more than 3, excess kurtosis. And you see that the peak is more sharp, and you see even the tails, right? So kurtosis and skewness are giving us an idea about the shape of, by the way, guys, we still have like 5 minutes, so I don't see why you're packing your things.
It's I need to prepare myself for that.
Yeah, 5 minutes you can prepare. I just want to finish normality. 5 minutes. You can go if you want. You watch the video, right? So skewness and kurtosis are giving us an idea of the shape of the distribution. Sorry, guys. Don't mind me. So when you bring together skewness, kurtosis, and sample size, you can perform Jagbera test if use is doing it for us. And with the Jagbera test, you know the null hypothesis is telling us that normally distributed. Alternative is telling us that not normally distributed. So we perform the test. You just check probability value, and you can make the test.
And you can check it in the graph from the line.
Yeah. So here they say normal distribution. Kurtosis is 3. I told you already. Okay. So you can read these things very easy. So of course, you know, to test for normality, we are using Jagbera test. And you see here, they talk about skewness and kurtosis. Actually, the Jagbera test brings all of them together, right? You see this T here stands for sample size. So Jagbera test is bringing skewness, kurtosis, sample size together, and is trying to calculate a Jagbera test statistic, which can help us perform the test. Okay, 2 more slides. By the way, guys, if you ask me that if you find a problem of normality, that is, the residuals is not normally distributed, how can you solve it? The only thing I can think of is sample size. Increase your sample size, because the more you increase the sample size, most probably your data and your residuals might be normally distributed because of central limit theorem. So try to increase the sample size. Okay. I think I will end in slide 40. Okay, slide 40. I think I should let you go. You're tired. Ikra is hungry. She's not fasting. You're from work. You're fasting, right? Ah, sorry. By the way, I should stop recording. So, guys, see you on Friday.
So,